Hi, this is Ms. Fitzmaurice, and this video is about waves. So by the end of this video, you should know the definition of a wave and wave speed. And you should also know the definition of a standing wave and be able to use that to identify the harmonic the standing wave is in and use that to calculate wavelength. Alright, so in the Slinky lab, you made two types of waves, transverse and longitudinal. And the definition of a wave, whether they're transverse or longitudinal, is that a wave is any time energy rather than matter moves through an object or moves through a distance. And you might say that doesn't make any sense. You know, when I did the Slinky wave, my Slinky was physically moving, and that's right, but it always ends up in its same place. So this coil that I just circled, it might go up to here and then back down, but it always ends up back in the same place. It's never going to end up all the way over here. So it's not traveling in the direction of the wave. Same with this coil. It might go here and then back, but it doesn't end up on the other side. So that's the definition of a wave, and I'm going to get rid of all these dots. Now we need to talk about a few features of waves, and you should already know a lot of these from pre-calc and sort of from simple harmonic motion, but we need to sort of formally define them. The distance it takes for a wave to repeat itself is the wavelength. Okay, so here is an example of wavelength. Okay, the wave goes up and then back down. The symbol for wavelength, which you probably saw when you took chemistry, is this Greek letter lambda, and the unit is meters. So this is called lamb, like Mary had a little lamb, duh. And then on a longitudinal wave, this would be the wavelength. Okay, or this would be a second wavelength. Also, you know, we talked about this in simple harmonic motion, but half the height of a wave is called the amplitude. And the symbol for amplitude is just A. It is also in meters for a transverse wave. For a longitudinal wave, the symbol or amplitude is also a thing, but it's in tension. Okay, so we also said we were going to talk about wave speed. And wave speed is, say you sent one pulse, okay, how long is it going to take this one pulse to get down to the other end, okay, or how fast is that going? And so V is, of course, our wave speed, our velocity. That's going to be in meters per second. Lambda here is our wavelength, and that's going to be in meters. And then just like in simple harmonic motion, we have frequency here. And frequency is in hertz, but hertz is really the same as 1 divided by seconds, because it's the number of times per second a wave repeats itself. And so what we end up having is velocity is equal to meters times 1 over seconds, which is the same as meters per second. So one thing that we're going to focus on, and you probably encountered this when you were doing your Slinky lab, are these things called standing waves. And standing waves are waves where some parts of the wave, so I'm kind of, imagine this is a Slinky and you're looking down at it, And some parts of the wave stay in the same place. They never move. And we're going to call these parts nodes. Okay, they stay in the same place. And there are these other parts, okay, and I'm going to highlight them here and here and here, and they are continuously moving back and forth, okay, and these ones are called antinodes. They're the opposite of nodes, and they move back and forth. So, maybe this is one snapshot in time, and then at the next moment, you see the nodes are staying in the same place, but the antinodes have moved slightly inwards. Okay, and maybe at the next moment in time, it'll just be completely flat. The antinodes have moved all the way towards the middle, but the nodes are still in exactly the same place. And then at the next moment, so they're traveling, the antinodes right now are traveling this way, up, up, down, down, up, up, and at the next moment, they might look like this. The nodes are still in the same place, and the antinodes have moved upwards or downwards, depending where they are, but away from their original position. And then lastly, they would get to exactly opposite from where they started. And notice that the whole time, the nodes have stayed in exactly the same place. Okay, but the antinodes are moving back and forth and back and forth and back and forth. So if you were in an earthquake, and there was an earthquake wave coming towards you, if it was a standing wave, which it might be or it might not be, you would not want to be on an antinode. You would want to be on a node because your house wouldn't be moving up and down. If you were on an antinode, your house would be moving the maximum up and down possible. And so when you were playing around with the slinkies in the Slinky Lab, you probably also found that depending on how fast you moved your slinkies, when you formed this pattern, you could form simpler, like really simple. You could just have two nodes and one antinode, or slightly more complex where you have 3 nodes and 2 antinodes, or if you moved your slinky even faster, you could form 4 or 5 or 6, and the number of nodes or antinodes are called different harmonics. So the next thing you need to do, and we'll talk a little bit more in a few days why it is that standing waves are formed, but you need to be able to sketch wave harmonics. And there are 2 types of standing waves that you'll see. There's standing waves where the medium is closed at both ends, or fixed at both ends. And I can't spell ends while I'm talking. An example of this would be 2 people holding a slinky, but also, since we're going to be getting into musical instruments, think about a guitar or a violin or any string instrument. Where literally the string is attached to the instrument at both ends. Okay, And the other type that we're going to be dealing with is open at one end and then closed at the other. And examples of this are like flutes, organ pipes, okay, most wind instruments. And when things are closed at both ends, if you can imagine, when a standing wave is formed, each end has a node at it. So for the closed at both ends, nodes at both ends. And when it's open at one end, you have node at one end, and then an antinode at the other. And that should say node, not antinote. And so depending on how many waves are formed, we call the patterns different harmonics. So if things are closed at both ends, okay, I said I need to have a node at each side, so the simplest possible pattern that you could get is just one loop, and we call that the first harmonic. Okay, and if you have two loops, that's the second harmonic. And if you have 7 loops, 1, 2, 3, 4, 5, 6, 7, and I'm terrible at drawing, that would be the 7th harmonic. Now, this is a little bit tricky, but when you think about harmonics, you need to think about how many waves. Okay, and we know that one wavelength you have to go up and down, so at any snapshot in time, say we're right at this snapshot, this is only half a wave. To have a full wave, it would extend out here. Okay, so the first harmonic, if something is closed at both ends, is 1/2 of a wave. The second harmonic, it goes up and down, so that's 1 wave. And the 7th harmonic is 1, that's 1 wave. Here's a second wave, here's a third wave, and a half. So we have 3.5 waves. Okay, it's a little different when you have a node and an antinode. So the first harmonic is just going to be the simplest possible pattern where we have a node at one end. So this is our node, and an antinode at the other. So that's our first harmonic. And this is actually 1/4 of a wave. And the second harmonic, it's the second simplest pattern where we have a node at one end and an antinode at the other. So this is our second harmonic. And this is 3/4 of a wave. Okay, you can think of each loop as half of a wave. Okay, so this is 3/4 of a wave in our second harmonic. And if we had the fifth harmonic, I want you to try to draw that right now and tell me how many waves. So the fifth harmonic would look like 4 loops. 1, 2, 3, 4. And it sounds like my dinner's ready. So the fifth harmonic would look just like this. And if you notice, we basically add an additional half loop for every harmonic, but we are still starting with a node and ending with an antinode. And harmonic, if you want to count the number of waves, so every 2 loops is a wave. So we have 1 wave, 2 waves, and then half of a loop. So that's 2.25 waves. And the reason it's important to be able to count the number of waves is that we need, in order to find the frequency, and if you're playing a musical instrument, the frequency corresponds to the pitch you're hearing. In order to find the frequency, we have to find the wavelength. So the next thing we're going to talk about is how to find the wavelength if you know the length of your instrument or the length of a string and which harmonic you're in. So in general, if you want to find the wavelength is going to be the length of your instrument or rope or whatever it is divided by the number of waves. Okay, so I'm going to give you a couple examples. Let's say that I have a string and I know that my length is 0.5 meters, not 0.05 meters, but 0.5 meters. And I want you to try to find me the wavelength in the following set of circumstances. Okay, so let's assume, even though I'm bad at drawing, that the length in all of these circumstances is 0.5 meters. And I want you to tell me what is the wavelength in each circumstance. Alright, so in our first situation, we have 1/2 of a wave. So our wavelength is going to be 0.5 divided by half of a wave. 0.5 divided by 0.5, which is 1 meter. Okay, in our second situation, we have, again, 0.5 as our length, and then we have 1.5 waves, so we have 0.5 divided by 1.5, and we get a wavelength of 0.33 meters. Okay, the last one, we have 1, 2, 3 whole waves, and so our wavelength is equal to 0.5 divided by 3, which is the same as 1/6, or 0.167 meters. Okay, and by the way, this is the first, third, and sixth harmonics of something that is closed on both ends. So what I want you to do is I want you to open up to page 23 of your Unit 7 packet. So this is page 23. And I want you to go ahead and try number 3 and then check back in for the answer. Okay, so now that you have tried number 3, it says a 2-meter pipe in a church organ is open at one end. So we know L is equal to 2 meters, and we know it's open at one end. In A, we just want the standing wave with 2 nodes. So we have one node right here, 2 nodes. It has to be open at both ends. So here is my wave, and this is the second harmonic. Okay, B, we want the wavelength that we just drew. Okay, we know that that's going to be the length divided by the number of waves, so we have 2 divided by 0.75 waves, so 2 divided by 0.75, which is 2.67 meters. In part C, we want the frequency, so we know V equals lambda F. They tell us that V is 340, and we know that lambda is 2.67 times F, so our frequency will be equal to 127.3 hertz. And then D, would you expect this to be the main harmonic that you hear? And the answer is no. You usually hear the first harmonic.